right, everyone, let's get started. I want to thank you all for joining us today. We're happy to have you. My name is Sharon White. I'm with BLT. You might know us better as Bottom Line Technologies. BLT provides custom electronic solutions, particularly but not limited to commercial and government aerospace applications. We design custom chips, embedded software, circuit boards, and complete systems. And we also offer live training for Xilinx and FPGA-related courses. And as always, our classes are taught by engineers for engineers. And that's what brings us here today. Today's one-hour session is all about Vitis. We'll explore the Vitis Unified Software Platform, look at the Vitis tool flow for on-premises, cloud, and edge deployment, and see how the hardware acceleration boosts performance. We'll also learn about the frameworks supported by the Vitis AI, including Caffe, TensorFlow, and Pytorch. And lastly, we'll go over the Vitis accelerated libraries. Today's speaker is going to walk us through all of this, accelerating AI with the Vitis Unified Software Platform. And that's why I'm excited to introduce to you Glenn Langan, one of our project engineers here at BLT. Glenn is an embedded autonomy and robotics expert. His skills include engineering guidance, navigation and control, or GNC, software, and electronics for autonomous systems. Over the past several years, he has been the technical lead for several USV and UAV projects, primarily for the Navy, that involve the careful coordination of the requirements for software, hardware, and electronics. He also has extensive experience with using and managing teams using a wide variety of embedded hardware, middleware, IDEs, build tools, and libraries. Welcome, Glenn.
Good to be here.
But before I turn it over to you, Glenn, I just want to let everyone know that this webinar is being recorded. We'll send you that recording as soon as we have it ready, so please look for it in your email. And we'll also be doing a Q&A session at the end, so I encourage all of you to use the chat panel on the side of your screen to ask questions as we're going through. We'll do our best to get to all of them at the end of today's presentation. Again, thanks, Glenn, for taking the time to talk to us about the Vitis Unified Software Platform. I know you have a lot to talk about in our short time here today, so I'm going to go ahead and turn it over to you.
Thanks, Sharon. Let's start off with a review of our goals for this webinar. We'll be looking at how to accelerate AI applications using the Vitis Unified Software Platform in 4 parts. First, we'll go over an introduction to the tool itself and how it's used to add hardware acceleration to your designs. Then we'll look at the deep learning framework supported by Vitis. And finally, we'll review the Vitis accelerated libraries and some of the accelerated functions that they provide. Once we've completed our review, we'll have a Q&A section for our remaining time. Make sure to leave any questions you have in the chat, and we'll try to get to as many as we can in this last section. Vitis Software Platform. Shown here is an abstracted model of the acceleration platform. And the Vitis Core Development Kit and application program is split between a host application and hardware accelerated kernels with a communication channel between them. On the left-hand side, we see the stack for the processing system. This includes the host application and all of the underlying libraries and drivers to talk to the hardware. The processor could be an x86 processor, or for embedded applications, an ARM processor. Now on the right-hand side, we have the hardware accelerated kernels that run within the programmable logic or PL region of a Xilinx device. Now on the host CPU, the custom application interacts with the FPGA using API calls, such as in this example, OpenCL. The API calls are managed by the Xilinx Runtime Library, or XRT. And these API calls are used to process transactions between the host program and the hardware accelerators. The communication link between the CPU and the FPGA shown here as PCI Express. That's typically what it'd be for applications such as data center applications. However, for applications that use an embedded platform, this would be an AXI interface. Now, control information is transferred between specific memory locations in the hardware, but data is transferred in and out of global memory. Let's look a bit about the differences between the global memory and the host memory. Now, global memory, it's accessible by both the host processor and the hardware accelerators. However, host memory, as shown on the left, is only accessible by the host application, shown here. Now, for a typical application, as an example, data to be operated on would reside in the host memory and is transferred from the host memory to global memory by the host application. The kernel then operates on this data and stores the results of the operation back into the global memory. Upon kernel completion, the host then transfers the results back into the host memory. Now at the lowest level, drivers handle the PCI Express transfers between the two devices. The FPGA comes preloaded with all the necessary logic to DMA data into the local DDR memory. The custom application kernels can then read this data, process it, and write it back to DDR using standard AXE4 interfaces. Now let's look a little bit into hardware acceleration. Now we see here we've got functions 1 through 5, and the first example up top we can see when all of these functions are run in series on a CPU. And we can see that function 2 is taking up much more than its fair share of time to execute. Now we can see down below an accelerated version of this where, depending upon your application, you can offload the functions that have high processing requirements that take a long time to the FPGA, and you can run some functions in parallel on the FPGA. We see here function 1 running on the CPU, and function 2 and 3 execute in parallel in the hardware. The output of function 3 goes to function 4, and then the output of both 2 and 4 provide the input to function 5 running back on the CPU. So with hardware acceleration, massively parallel execution within and across functions can be achieved. However, the question is, what handles this acceleration? The ACAP, or Adaptive Compute Acceleration Platform, handles compute-intensive, deeply pipelined, and massively parallel operations. The CPU then handles the rest. Xilinx devices offer many advantages over traditional CPU-GPU acceleration, including implementing any function that can run on a processor, resulting in better performance at lower power dissipation. As we've learned in previous slides, an application program is split between a host application and hardware-accelerated kernels with a communication channel between them. The build process then follows a standard compilation and linking process for both the host program and the kernel code, as shown in this diagram. And we can see that we start off with the source code, C, C++ with an OpenCL API for the host application on the left, and on the right for the FPGA kernels, either RTL or C++, or C, C++. Then the compilation and linking process occurs, and the result is an application executable that can run on the CPU, .exe for example, and on the FPGA, an FPGA binary, a .xcl bin. So now let's look at the Vitis development environment. The Vitis Unified Software Platform is a tool that combines all aspects of Xilinx software development into one unified environment. The Vitis Software Platform supports both the Vitis Embedded Software Development Flow, and this would be more familiar to those familiar with the Xilinx Software Development Kit, or SDK, and alternatively the Vitis Application Acceleration Development Flow. Users can design accelerators for data and compute-intensive applications at the edge, on premises, or in the cloud. The Vitis Application Acceleration Development Flow provides a framework for developing and delivering FPGA-accelerated applications using standard programming languages for both software and hardware components. For FPGA-based acceleration, the Vitis Core Development Kit lets you build a software application using an API, such as the OpenCL APIs we've been using in previous examples. And this would be used to run hardware kernels on accelerator cards, such as the Xilinx Alveo Data Center accelerator cards. The Vitis Core Development Kit also supports running software applications on an embedded processor platform, running Linux, such as the Zynq UltraScale Plus and PSOC devices. For the embedded processor platform, the Vitis Core Development Kit execution model also uses the OpenCL API and the Linux-based Xilinx runtime to schedule the hardware kernels and control data movement. Now, the Vitis environment also supports debugging and profiling your application. The Vitis Analyzer, shown here, is a utility that allows the viewing and analyzing of reports generated both while building and while running the application. The IDE supports both GUI and command line users and is based on the Eclipse open source standard. Now, the Vitis Unified Software Platform is an integrated development environment for the development of embedded software applications targeting Xilinx embedded processors. The Vitis environment keeps the features of the software development kit and adds more to address the requirements for heterogeneous computing. The Vitis technology targets acceleration hardware platforms such as the Alveo Data Center Accelerator cards, or the Zynq UltraScale Plus MP-SoC and Zynq 7000 SoC-based embedded processor platforms. The Vitis runtime provides an API and drivers for your host program to connect with the target platform and handles transactions between your host program and accelerated kernels. The Vitis Core Development Kit provides the software development tool stack, such as compilers and cross-compilers, to build your host program and kernel code, debuggers to help you locate and fix any problems in your application, and analyzers to let you profile and analyze the performance of your application. Vitis accelerated libraries provide performance-optimized FPGA acceleration with minimal code changes and without the need to re-implement your algorithms to harness the benefits of Xilinx adaptive computing. Vitis accelerated libraries are available for common functions such as math, statistics, linear algebra, and DSP, and also for domain-specific applications like vision and image processing, video transcoding, quantitative finance, database data analytics, and data compression. For more information on the Vitis accelerated libraries, you can go to the URL xilinx.github.io/Vitis_libraries. So let's briefly look at a more accurate depiction of hardware acceleration. We can see here the API calls are used to interact through with the FPGA accelerator to run function 2, shown at the bottom. The data transfers between the host and FPGA happens through the PCI Express interface, shown with the read and write executions in the middle line. In the case of the embedded flow, this would be through the AXI interface. So here's some rules to remember when designing your hardware acceleration. The first rule, remember Amdahl's law, which we'll be looking at. Rule 2, target large compute-bound tasks. Rule 3, know your ceiling. And Rule 4, think throughput, not only latency. So Rule 1, Amdahl's law. So you need to consider the performance of your application and not just individual functions. You want to optimize the application and not focus on improving the performance of one function that doesn't have a large impact on the overall application. You would start by measuring the runtime and throughput performance to identify the bottlenecks for your application, and then these performance numbers should be generated for the entire application as well as for each major function in the application. The most effective way to do this is to run the application with profiling tools like valgrind, callgrind, and GNU gprof. The functions that consume the most execution time are good candidates to be offloaded and accelerated onto FPGAs. And we can see here depicted in the slide that it's better to accelerate function 2 by 2 times since it takes such a large time to execute than to really optimize function 3, improving by 50 times, but it's such a small function that does not have a major impact on the application as a whole. So Rule 2, target large compute-bound tasks. So for this, you want to look for functions where compute time is much greater than the data transfer time. Functions that perform a lot of processing per invocation are preferable over small functions that are called many times, and this in large part is due to the added latency of the data transfers and the API calls. Rule 3, know your ceiling. Data needs to be transferred at the right time, otherwise the application performance is negatively impacted if the kernel needs to wait for data to be available. Therefore, to counteract this, it's important to transfer data ahead of when the kernel needs it. This can be achieved by overlapping the data transfers and the kernel execution. And rule 4, think throughput, not only latency. As an example, when determining optimal buffer sizes, you'd want to consider the effect of large buffers on resource utilization and transfer latency. And another goal to keep in mind is to reduce CPU idle time, shown by the gap on the first line, and to maximize the kernel execution. Now we'll be moving on to part 2, looking at the framework supported by the Vitis AI development environment. First, let's go over what a deep learning framework is. A framework provides a streamlined interface for developers to build machine learning models without needing to learn all of the details of the underlying algorithms. The framework provides a software environment within which users can train, optimize, and deploy their models. A framework provides a clear, concise way for defining machine learning models for deep learning applications, using a collection of open source, pre-built, optimized components and toolchains. The Xilinx Vitis AI development kit supports high-level deep learning frameworks such as Caffe, TensorFlow, and Pytorch. Pytorch is a beta release in the Vitis AI Environment 1.2 version. Now let's take a look at what a network or model is and which models are supported by the Xilinx Vitis AI development environment. Models are built using machine learning algorithms based on the sample data, also known as training data. The models are then used to make predictions without being explicitly programmed to do so. For example, the residual network, or ResNet50 model, uses the TensorFlow framework for performing image classification. The trained models are efficient CNN-based deep learning architectures, which consist of multiple layers between an input and an output. All near-to-correct mathematical manipulations are performed to turn the input into the output, irrespective of a linear or nonlinear relationship. Xilinx provides 60-plus Caffe, TensorFlow, and Pytorch pre-trained models. The Vitis Model Zoo repository includes optimized deep learning models to speed up the deployment of deep learning inference on Xilinx platforms. These models cover different applications, including advanced driver assistance systems, autonomous driving, video surveillance, robotics, data center, and so on. You can get started with these free pre-trained models to quickly start integrating deep learning acceleration into your designs. Currently, there are 64 models available. The models are optimized with pruning, making highly optimized models available for quick development. Vitis AI Environment 1.2 provides 8 newly added Pytorch models, as well as test and training code for them. You also have the option to retrain using a custom dataset. The Model Zoo includes comprehensive information about each model, including applications, frameworks, training and validation datasets, backbones, and input sizes. The Vitis Model Zoo makes it easy to quickly deploy with pre-validated models to measure the quantization accuracy and to find the latest AI model resources. You can download and extract the model archive to your working area on your local hard disk. As an example for a Caffe model, you should see the directory structure shown on the slide. And an example for a TensorFlow model. And finally, the third framework for a Pytorch model. This is the directory structure. You'll see there's several commonalities, but there are a couple of differences with the files between the different frameworks, and we'll be going over that in more detail. Here we see a list of some AI applications and the models associated with them. We've got image classification, autonomous driving, smart city, smart traffic, smart retail, and medical. Now to look at each of the frameworks in more detail. And the first one, Caffe, stands for Convolution Architecture for Feature Extraction. Developed by UC Berkeley, it's an open source framework with developed models and worked examples for deep learning applications. It's an open source project with pure C++ or CUDA architecture, which has helped to build up a large community of contributors. Multiple software interfaces are available for supporting different applications, with command line, Python, and MATLAB interfaces available. Included are pre-processing and deployment tools, as well as reference models and examples. The project is fast, well-tested, and extensible, making it ideal for both research experiments and industry deployment. Caffe can process over 60 million images per day on a single GPU, to give you an impression of its speed. Now we'll look at some of Caffe's data management and pre-processing features. Data can be ingested in a number of formats, such as level DB or LMDB, which allows for efficient loading of data into the model. Data can be directly ingested from the main memory if C++ or Python are used. Caffe also supports importing raw image files in hierarchical data format, or HDF5, which helps to store and organize a large amount of data efficiently. HDF5 data does not support data transformation as is. Users need to pre-process the data with any desired transformations before feeding it in. Caffe supports pre-processing command line tools, which helps with dataset creation from raw images, with splitting the dataset into training and validation, and with mean image generation. Caffe supports processing data to make it available in the proper form when needed, which can be used for training purposes. Cropping or resizing an image to focus on the region of interest, for example. A model created using a Caffe framework consists of terms such as the blob, which is an n-dimensional array for storing and communicating the data. It holds data, derivatives, and parameters of the model. A layer is a fundamental unit which connects and transforms the bottom blob into the top blob, for example, via convolution, pooling, and so on. A net is a set of layers and their connections that computes gradients via forward or backward propagation. And finally, a solver uses the forward and backward gradients to update the weights and optimize the model. Caffe stores and communicates data using blobs. A blob provides a unified memory interface for holding a datum. Blob size is denoted as n times c times h times w, where n is the batch size number, c is the channel, h is the height, and w is the width. The next of the frameworks we'll be looking at is TensorFlow. TensorFlow is an open source software library for high performance numerical computation using data flow graphs. TensorFlow was developed by the Google Brain team for internal use. It has intuitive high-level APIs that enable building and training any type of machine learning model. It's widely used in an open source framework, with many users contributing by creating and adding tutorials and examples. It has a simple and flexible architecture that enables users to deploy computation to one or more CPUs or GPUs in a desktop, server, or mobile device without rewriting the code. The training of massive deep neural networks can be complex and confusing, and to make it easier to understand, debug, and optimize, TensorFlow provides a suite of visualization tools called TensorBoard. TensorBoard visualizes a TensorFlow graph, plots quantitative metrics about the execution of the graph, and shows additional data like images that pass through it. Everything in TensorFlow is based on the computation graphs. The graph is the model in this case. The graph nodes represent the mathematical operations, while the graph edges connecting the nodes represent the multidimensional data arrays, or tensors, that flow between them. A tensor is best visualized as a multidimensional array. The tensors flow through the graph and are modified by the operations in the nodes. There are 4 properties to keep in mind when working with the tensors. There's the name of the tensor, the rank of the tensor, or the number of dimensions it has, the shape, or the size of the dimensions, and the data type. The operations usually manipulate or change the tensors by performing a mathematical function. Operations live inside the nodes of a computational graph as shown. Nothing happens in TensorFlow until you create and execute a session. A TensorFlow session object communicates between the Python code and the TensorFlow execution engine. The computational graph is also executed in the session. Now, the third of the frameworks we'll be looking at is Pytorch. Pytorch is an open source deep learning framework based on the Torch library and was developed by Facebook. It's a Python-based scientific computing package targeted to 2 goals. First, a replacement for NumPy to use the power of GPUs, and second, as a deep learning research platform providing maximum flexibility and speed. Pytorch uses dynamic computation graphs in contrast to TensorFlow's static graphs. The tensors are similar to NumPy's ND arrays, with the addition being that tensors can also be used on a GPU to accelerate computing. Let's look at some example code on the right for Pytorch. After the initial setup, the first call is to torch.empty. With the arguments 4 and 3, it constructs a 4x3 matrix named result. The matrix is created uninitialized, so it will contain whatever values were in the memory allocated into it at the time of creation. Next, the torch.add call adds the variables x and y, and then stores their sums in the matrix created with torch.empty. And this then replaces the uninitialized values that it had during creation. The print statement then prints the values in the result matrix. Now let's look at the different input files required at each stage of deployment for each of the three frameworks we've reviewed. For Caffe, the Vitis AI quantizer takes a floating point network model, a pre-trained weights file, and a calibration dataset as inputs to generate a lightweight quantized model. The files generated as outputs are a quantized network description file and a quantized model parameter file. For TensorFlow framework, the Vitis AI quantizer takes a floating point frozen graph, a calibration dataset, and the Python function input fn to read images in the calibration dataset and perform a pre-process on it. As an output, the tool will generate a quantized model for the Vitis AI compiler and a quantized model for evaluation. These files are in the PB format, which is an extended TensorFlow output format. For a Pytorch framework, the Vitis AI quantizer takes a pre-trained Pytorch model, generally a PTH file, a Python script, and a subset of the training dataset containing 100 to 1,000 images. Two important files will be generated, the name of the model.py, which is the converted Pytorch format model, and the name of the model _int.x model, which is the deployed model. The Vitis AI compiler compiles the models into one or more DPU kernels, which are ELF format files containing DPU instructions. The Vitis AI compiler can also generate other ELF files for operations that are not supported by the DPU and must be deployed and run on the CPU. The Vitis AI development environment offers a unified set of high-level C++ and Python programming APIs to support machine learning application development across Xilinx cloud-to-edge devices, supporting the Alveo U200 and U250 cards, the Alveo U50 and U280 cards, and Zynq devices. These APIs enable you to easily port deployed DPU applications from cloud to edge or vice versa. Next, we'll be looking at Part 3, the Vitis Accelerated Libraries. We'll be looking into how software developers can build accelerated designs by utilizing the Vitis Accelerated Libraries. These libraries can be used plug and play as is, or used as the starting point for building custom accelerators. This is done using the Vitis Unified Software Platform, which integrates the user application, the accelerated libraries, and any custom accelerators in order to deploy the design to an FPGA, SoC, or ACAP device. The Vitis Software Development Platform includes an extensive set of open-source, performance-optimized libraries that offer out-of-the-box acceleration with minimal to zero code changes to existing applications. Provided is a broad range of pre-optimized libraries that can be integrated as software APIs in order to bring plug-and-play acceleration to your applications. As mentioned in the last slide, you can also customize these libraries to design your own accelerator. Common Vitis libraries for math, statistics, linear algebra, DSP, and data management offer a set of core functionality for a wide range of applications. Domain-specific Vitis libraries offer out-of-the-box acceleration for workloads like vision and image processing, quantitative finance, database and data analytics, and AI and data compression. This list continues to expand with every release. There are three types of implementations provided by the Vitis libraries: L1 primitives, L2 kernels, and L3 software APIs. These implementations are organized in their corresponding directories L1 through 3. The L3 software APIs provide C, C++, and Python function interfaces to allow pure software developers to offload specific accelerated functions to pre-built FPGA kernels, also called overlays. The L2 kernels are HLS-based pre-designed kernels that can be directly used for FPGA acceleration of applications on integration with the Xilinx Runtime Library, or XRT. This requires L3 host code and is built with the Vitis tool. The L1 primitives can be used by developers working on hardware design implementation or designing hardware kernels for acceleration. L1 primitives are particularly suitable for those familiar with hardware design. And we can see that with each layer, the abstraction is increasing between the hardware and the software. At the L3 level, the Vitis accelerated libraries provide interfaces to familiar and commonly used programming languages like C, C++, and Python. This enables you to use the Xilinx platforms to accelerate your applications without drawing focus away from developing the more application-specific pieces of your code. Regardless of the targeted application platform, be it an x86 host or a Xilinx embedded platform, the Vitis accelerated library APIs and kernels provide the same level of abstraction as using any software library. The Vitis libraries are accessible to developers through GitHub and scalable across all the Xilinx platforms. Applications developed using these optimized libraries can be deployed to Xilinx platforms at the edge, on premises, or in the cloud without having to re-implement the accelerated application. The Vitis libraries can be used as plug-and-play accelerators for rapid prototyping and quick evaluation. They can be called directly as an API for workloads such as computer vision and image processing, quantitative finance, database, and data analytics. The Vitis library functions can be used as optimized algorithmic building blocks to design custom accelerators for your application. You can modify them to suit your specific needs, or you can use them as a reference to design your own. Now we'll look at a few specific libraries. Listed here are some of the L1 APIs and L2 APIs for the Vitis database library. The library is an open source C++ release released under the Apache 2.0 license. These APIs can be used to accelerate SQL engines utilizing the FPGA for query execution. And you can see for these libraries, the link for more information is provided at the bottom right. Listed here are some of the library classes for the quantitative finance library. It is also open source and is designed for modeling, trading, evaluation, and risk management for financial applications. Again, documentation on the bottom right. The Vitis Vision library is optimized for the Zinc 7000 SoC, Zinc UltraScale Plus MP SoC, and PCI Express interface-based Vertex FPGAs and U200 devices. The library provides a software interface for FPGA acceleration of computer vision functions. The Vitis Vision library functions are similar in functionality to their OpenCV equivalents, with any differences between the two provided in the documentation function by function. Here we see a list of some member functions and descriptions for the Vitis Vision library and the link to the online documentation. Next, we have an overview of what's available for the Vitis Data Compression Library. The library is again open source C++ and can be used to accelerate data compression algorithms. The Vitis Security Library provides optimized hardware implementations of the more common security algorithms. This includes symmetric block cipher, symmetric stream cipher, asymmetric cryptography, cipher modes of operations, message authentication code, and hash functions. These are all provided as L1 primitives. The The Vitis BLAST library is a fast FPGA-accelerated implementation of the standard basic linear algebra subroutines, or BLAS. All three implementation layers are provided: the L1 primitives, L2 kernels, and L3 software APIs. APIs are provided with C, C++, or Python interfaces at the L3 level, allowing you to quickly swap them into your application. These APIs can be used to accelerate functions for a wide array of applications, including machine learning, computer vision, quantitative finance, and more. The Vitis Utility Library is an open source library that can be used as an aid when setting up streaming and storage access. The goal is to provide efficient interfaces for accessing memory in DDR, high bandwidth memory, or ultra-RAM, and for performing data distribution, collection, reordering, insertion, and discarding for stream-based transfers. For the utility library, we can see here a list of APIs in the L1 module and some examples of the memory access that's supported on the right. These APIs can be used to abstract memory access in the application code, allowing more of the focus to be on developing the application's core functions. The Vitis DSP library provides L1 through 3 primitives for digital signal processing. It provides a synthesizable super sample data rate, or SSR, FFT, implemented as a C++ template function. Template parameters can be used to adjust the default settings of the FFT architecture, with the list shown on the slide. And again, documentation is on the bottom left. And now we have the Vitis Solver library. This provides L2 APIs for matrix decomposition operations, linear solvers, and eigenvalue solvers. The Vitis Graph library is a C++ open source library for accelerating graph applications for use cases such as machine learning, genomics, search engines, and social network analysis. It currently covers the predefined kernel level L2 acceleration and will evolve to offer the module level L1 and software API level L3. And finally, we have the Vitis Data Analytics library. Some of the performance-optimized functions to accelerate data analytics pipelines are shown here. This library is again open source C++ and includes both L1 and L2 primitives. Using the L2 HLS C++ APIs, advanced users can easily adjust the logic to suit their specific needs. And with that, we've concluded our review of accelerating AI with the Vitis Unified Software Platform. We did an overview of using the Vitis Unified Software Platform to boost application performance with hardware acceleration. We reviewed the 3 deep learning frameworks supported by Vitis AI, Caffe, TensorFlow, and Pytorch. And then we reviewed the Vitis acceleration libraries and the wide array of accelerated functions they provide, with implementations at the hardware primitive, HLS kernel, and software API levels. Thank you for your time, and with that, I'll hand you back over to Sharon.
Great, thanks Glenn. That was really useful information. Just a couple of things before we get to the Q&A. I know we have a couple of questions that we want to get to, and folks, if you have any questions, please go ahead and drop them into the chat panel now, and we'll do our best to get to everything. As a reminder, we have some classes coming up that if you're interested in Vitis, you might be interested in as well. Vitis is a newer tool from Xilinx, and we have several classes on its capabilities and how it can fit into your projects. The latest Xilinx architecture, Versal, is supported by the Vitis tool. We offer several AI engine classes, a NOC class, and an architecture class. In fact, Designing with the Versal AI Engine 1, Architecture and Design Flow, is coming up on August 4th and 5th, and Glenn will be teaching that class.
Yeah, if any of you could attend, that'd be great.
If you're interested more in System on a Chip in relation to Vitis, our Embedded Systems Hardware Design Bootcamp is a great option and includes Vitis Labs. I'll go ahead and drop those links into the chat panel for you in case you're interested in those. If you have any questions about them, please reach out to our training coordinators. I'll put that information into the chat for you as well. And another reminder that this webinar is being recorded, so we'll go ahead and send a link to you with the recording as soon as it's ready. That way you can go back and listen to any information you might have missed. And if you liked this webinar and are interested in future topics, you can sign up on our website to receive emails about our upcoming webinars. Our next webinar will be on debugging, and that's coming up in September. Okay, so without any further ado, let's get to the Q&A.
All right, Glenn, we have our first question, which is what type of applications do you think best take advantage of the new hardware in Versal?
All right, so Versal, that's a good question. It's some of the latest hardware from Xilinx, and it's very interesting. We're familiar with SoC devices, system-on-chip devices from Xilinx, but this is a new take on that, the Adaptive Compute Acceleration Platform. It takes in all of the benefits of the SoC-based designs and adds an additional component, a scalable 2D array of vector processors, and it can be very useful for AI applications and signal processing. And it's very handy how it's all in one embedded device. So I would say the answer is that it's very good for any edge applications where you want everything in one package. And it really fits that role very well. It's very exciting. Really, it's kind of, think of it as the next generation of this style of device. And yeah, as Sharon mentioned, there'll be some courses on it coming up if anyone's interested in learning more about it. I guess my short answer is signal processing, particularly things like 5G and the upcoming advances to Wi-Fi, and of course, image recognition and other machine learning applications at the edge.
All right, Glenn, our next question is, even though there's already Vitis APIs, can I use Vitis primitives directly in my code instead?
Yes, you can. As we talked about, there is the level 1 through 3 options for interacting through Vitis, and the level 1 is the primitive. So you can either use one of the ones provided by Xilinx as part of their acceleration libraries, or you can create your own primitive or use an existing primitive at that layer in Vitis.
All right, our next question is, how is the floating point to fixed point conversion handled when migrating a SW function to FPGA? And then the second part, if implementing floating point on an FPGA, how do you handle floating point error codes?
Okay, that's a good question there. So it does come down a lot to your specific application and what IP you're using, what your software is doing. In many cases, what this would end up looking like is you'd be passing in the IEEE floating point format to your FPGA application, and then you would need to handle it there. However, if you're using a provided IP, then you'd obviously need to look at the documentation and confirm what format is expected and what features it has to handle things like that. Generally speaking, that would be preferable to try to handle as much floating point operations in software as possible. Any conversions that need to happen, do those in software. But again, it's going to vary depending upon what IP you're using.
All right, our next one, which of these three frameworks, TensorFlow, Caffe, and Pytorch, is the most popular or supported on Xilinx devices for image recognition applications?
Well, they're all supported. I would say that Caffe has the best documentation for usage with the Xilinx tools, but all three are perfectly good options.
All right, next up, would Versal ACAP be good as advanced PLC?
That's another good question. It's not something that I've thought about specifically. I would say yes, it does have a lot of the features that you would use in advanced PLC. In some cases, you might be able to get away with something that doesn't have as many features. So again, it depends on your application, but I would see for a lot of applications, that'd be a perfect fit for it.
Okay, this isn't quite a question, so maybe you can help us out here, Glenn. I have an Alveo U200, which is not working on TensorFlow for object detection. Any thoughts?
Yeah, for that one, I can't say I can think of any obvious off the top of my head reason why you'd be having a problem there. I would really need more information to give much feedback on that. There's obviously a lot of steps where problems could occur. You know, has everything been deployed properly? Is the training succeeding? Yeah, I would need to get more information on that one, but we may be able to help with that if you get in contact with our design team. That's all I can really provide right now live. Sorry.
All right, next up. So where does your traditional RTL designer fit into the design process for Vitis? And do we build platforms for the SW system engineers to leverage?
So all of the traditional workflows should be supported. Everything that you're used to doing can be done. You just need to use the appropriate, L1 through 3 level to integrate your code. And so all of your normal processes will work for creating custom RTL code and other custom applications like that. And of course, as you mentioned, it is a valid option to build platforms using these tools for the software team to leverage. The structure of all this is designed to improve abstraction between the different disciplines. So it is possible to create a very pure software interface to the hardware. So there's added capabilities available through this tool, but it isn't going to interfere with using any of your existing design processes either.
All right, are there any other questions out there? All right, we'll wait just another minute or two. That way, if you guys think of anything else you want to ask Glenn, we're here. Go ahead and drop them. Oh, looks like we missed a question. So hang on 1 second. Let me read that to you. For L1, L2, and the L3 layers, can new L1 code be used inside an L3 layer, or are all the layers expected to be isolated?
So you wouldn't typically use the L1 code inside an L3 layer. Again, there's lots of variations, application to application, but what I would imagine you do if you have L1 code you want to leverage as in providing a software interface for it, you would create an overlay that would allow an API at the L3 layer to interact with that overlay. And that way you'd be able to provide an interface through to your L1 code at the L3 layer in a way that abstracts the software developers from any kind of hardware considerations.
All right, do we have any other questions out there? Yep, we have one coming in, Glenn. Hi, I use Xilinx's Zinc UltraScale Plus MP-SOC device for my development. Can I leverage zero copying between global and local memory?
That's a good question. It would rely somewhat on what the driver supports, and I'm not familiar with that particular capability. It's not one that I've used. I would check the documentation. My guess would be no, but that should be laid out in the documentation for the drivers. And you'd be using the AXI interface. since you've got the Zinc MP sock. Yeah, I would check the driver documentation on that. It should be all laid out there.
All right, any other questions? All right, everyone, thank you so much for joining us. If you like this webinar and want to join us for additional webinars, you can sign up on our website, that's bltinc.com, for our webinar series. The next one coming up is in September on debugging, and we'll also send out the recording. So if you're signed up for our webinar list, you will be able to get all of the information about our upcoming webinars and things that have happened. So go ahead and sign up if you'd like to. I will drop that link into the panel. Thank you, everybody, for joining us. I hope you enjoyed this webinar. Thanks, Glenn.
Thanks, Sharon. Good to talk to you all. Thanks for coming.